All right, so our first graph in physics, position versus time graphs. Now, this is the first of 6 or 7 graphs that we're going to have throughout the course of the year. And no matter what the graph is, no matter what, it starts out with position versus time, and then later this period we're going to look at velocity versus time, and then, in chapter 6 we're going to look at force versus time. There's multiple graphs. Do I want you to memorize what's important on each graph? Absolutely no. Do not memorize what's important. So on this graph, what's the important thing? Slope, the slope of a line is the velocity of the object. Do I want you to simply memorize that? I want you to do something better than memorize it. What's something better than memorize it? Understand it, which is what I'm going to explain. I'm going to explain why slope is velocity. So really the only thing you have to have memorized is the definition of slope. So what is the definition of slope? Rise over run. Okay, so let's look at a segment of this graph, O to A. So this segment right here. We're going to use this as our explanation of why slope is velocity. All right, what is the rise from O up to A? So this black line here is the rise. And I know it's 4, that's not what I'm looking for. But what is it? What is this rise right here? Well, what's on the y-axis? So see here, what's that x right there? The x measured in meters? X is the position. X is the position. So we'll write it out. The y-axis is position. The x-axis is time, just so it's super clear. All right? So what is this rise? Isn't it just the change in the position? The object starts at 0 meters right there and goes to 4 meters at point A. Everybody got that? The rise is the change of position. And what's another name of change? What's another name for change in position? The displacement. Now, what's the run? The time. It's the change in time. Okay? That should look familiar. Displacement over time is what? Velocity. So you can always figure out what slope is. You just go, okay, slope is rise over run. What's the rise telling me? Oh, the rise is the change of position. Okay, what's the run telling me? Oh, the run is the time. Oh, displacement over time is velocity. You figure it out. Everybody got that? Okay, now what's happening from O up to A? What can we say about that slope? It goes 4 meters in 4 seconds at a constant rate or not constant? Constant. So if you look at this line, the red line from O up to A, the slope of that line is constant. If the slope is constant, what does that tell us about the velocity? The velocity is constant. So O to A has constant velocity. And I want you to make a note of something right now. Another name for constant velocity is zero acceleration. If your velocity is constant, that means it's not changing. So what's the definition of acceleration? Change in velocity over time. If your velocity is not changing, then what's the acceleration? Zero. Another name for constant velocity is zero acceleration. That's really important. Okay? Now what's happening from A to B? Is A to B constant velocity? How do we know it's constant velocity? Because the slope is constant. In fact, What is the slope from A to B? 0. So what's the velocity of the object from A to B? 0. And you want to know why that makes sense? Because look, what's the position of the object from A to B? 4, and it's just sitting there. It's like you right now. All of you are just sitting there, not doing anything. Just, you're not moving. Your position is not changing. Okay? So A to B is also a constant velocity. It's a constant 0 velocity. Now, what's happening from B up to C? This is the trickiest part. From B up to C, is the slope constant? No. What's happening to the slope from B up to C? It's getting, the slope is getting bigger, bigger, bigger. If the slope is getting bigger, 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 that means the velocity is getting bigger, bigger, bigger. What's another name for that? Acceleration. So B up to C is an acceleration. Okay? Don't fall asleep. I see you. I'm watching you. Lights off, movie on. It's like watching a movie. Whenever I watch a movie, I fall asleep. I'm tired. My kids wear me out. Okay, so I'm going to go back to the original. Let's revert. Okay, so I have 3 questions for you guys. So I'll give you 3 minutes. Find the average velocity from point O to point C, instantaneous velocity at t equals 2, and the instantaneous velocity at t equals 9. So do your best on this, and then we'll go over it. All right, so to find, we'll start with the average velocity from point O to point C. So let's take off these other 2. All right, average velocity from O to C. Average is from one time to another time. Instantaneous is at a specific time, right? So if we're looking for the average velocity from point O to point C, we'll just notice, does the velocity stay constant from O to C? No. We have a constant velocity from O to A, 0 velocity from A to B, and then we have an acceleration from B up to C. So how do we find the average velocity from beginning to end? Well, what you do, so see this dotted line right here that's already been put there for us? If we take the slope of that dotted line from O up to C, that will give us the average velocity from O to C. And it makes sense because look, so average velocity, put a little line above the V for average. What is the rise from O up to C? 10 meters. You know, so that's the displacement over time. It's 10 meters. What is the run from O over to C? 12 seconds. So this comes out as 0.83 meter per second. That would be the average velocity. That would be the average velocity from O up to C. Now, did we have to use point O and point C to take the slope of that line? Because it's a straight line. If it's a straight line, you know, you can use any 2 points you want. We could have used this point right here and this point right there. Okay? You can, for a straight line, you can use any 2 points you want. All right. Any questions on that? Yeah. What's that? No, I put it in decimal form. In physics, the answers are typically put in decimal. I mean, a fraction wouldn't be wrong, but decimal is, you know, that's what you'll see in the back of the book. Yeah. For a straight line? Well, yeah, if you're looking for average velocity between 2 points, connect those 2 points with a straight line and take the slope of that straight line. And that'll be the average velocity between the 2 points. All right, second question. Let's clean this up. Okay, find the instantaneous velocity at t equals 2. So now we're not going from one point to another point. We're focusing in exactly at this point right here, at t equals 2. Now what happens to be there's something that's really nice about t equals 2. What's super duper nice?
It's at 2 meters.
It's right at 2 meters, yeah, but that's not what I'm thinking. Yo,
Has a constant velocity.
it's on a segment of the graph where the velocity is constant, right? From O to A, for this whole segment right here, the velocity is constant, right? So what about the velocity at t equals 1? Is that going to be the same or different as the velocity at t equals 2? Same. How about the velocity at t equals 3? Same. How about 3.5? Same. Anywhere on that line, the velocity is the same, right? So how do we go about finding the instantaneous velocity at t equals 2? We're going to take the slope of this line right there. And does it matter which 2 points we use to take the slope? Nope. If you're dealing with a straight line, you can use any 2 points you want. So let's use those 2 points. We'll just do that. So rise over run. So the instantaneous velocity at t equals 2. So what's this rise right here? 2, and the run is 2. So this gives 1 meter per second. So what's the velocity at t equals 1? 1 meter per second. What's the velocity at t equals 3? 1 meter per second. It's the same everywhere. Now, for the trickiest part, find the instantaneous velocity at t equals 9. So t equals 9 is right here. It's right on that curve. Now, how do you deal with a situation like this where you're finding instantaneous velocity on a graph that is not a straight line? Well, the first thing you have to do is draw in what we call a tangent line. Remember the definition of a tangent line? Touches the graph at only one point. So this line right here is the tangent line at t equals 9. This tangent line is for that point right there, which is t equals 9. If we take the slope of that tangent line that I just circled, the slope of that tangent line will be the velocity at that point where we drew the tangent line. That make sense? So let's use that point, we'll use this point, and that point. Hey, now are tangent lines highly accurate, or is there human error? There's human error. It's not meant to be perfect. It's more the technique. You know, you should be in the ballpark. It's not, you know, you guys aren't robots. There will be some error. So the velocity at t equals 9, we're taking the slope of the tangent line. So the rise is about 6. The run is from 3 over to 11, so that's about 8. So 0.75 is the instantaneous velocity at t equals 9. Our second graph is velocity versus time graphs. Now, no matter what the graph is, there's 2 possible things to analyze. Did I say that already? 2 possible things to analyze. What did we analyze on the first graph? Position versus time. We looked at slope. On a velocity versus time graph, there are 2 important things: slope and area. And all of you know how to find area. Base times height. That's how you find area. Okay, are you going to memorize what slope and area are for this graph? What's better than memorizing? Understanding it. So let's start out with slope. Let's figure out, how would you go about figuring out slope? Well, slope is rise over run. So let's look at this part of the graph right here. From 10 seconds to 15 seconds. From here to here. So what is the rise? I mean, I know it's 8. That's not what I mean. What is the rise telling us for this graph? It's the change in velocity, right? what's the velocity at 10 seconds? 0, right? At 10 seconds, the velocity is 0. What's the velocity at 15? About 8, maybe a little less. So the rise is the change in velocity. What's the run? The time. This should look familiar to you at this point. It's the acceleration. So the slope on a velocity time graph is acceleration. Don't memorize it, understand it. Now how about area? What would area be? Well, let's just look at this area here. I'm going to shade this. So how do you go about finding area? Well, since it's a triangle, we have to have 1/2, right? 1/2 base times height. So let's look at units here. What's the unit of this base right there? Time, which is measured in seconds. The base is measured in seconds. What's the height measured in? Velocity, which is meter per second. So look what happens here. What's going to happen to seconds? They cancel. The seconds cancel out, and you're left with meter. And what is meter a measurement of? Displacement. That's how we measure displacement. Displacement, delta x. But hey man, is displacement a vector? Meaning, does it have direction? It does. Where do we get direction from on the graph? Well, look, this shaded area here is positive. That's a positive displacement. How do I know that that's a positive displacement? Because the velocities are positive. If the velocities are positive, then the displacement's going to be positive. Okay? How about, let's do a shaded area over here. This area here would also be displacement, although that area is going to be a negative displacement. So by the way, just so you can wrap your brain around this, let's just draw a picture of what's happening here. So we got this car. Let's just say that this is a graph for a car. To the right is positive, to the left is negative. Which way does this car start moving at the beginning of the graph? The car starts out moving to the left, right? And it goes to the left, to the left, to the left, to the left, until when? Until t equals 10. Now what happens at t equals 10? So the car is way over here, right? At t equals 10, stops, and then what does it do at t equals 10? Starts moving to the right, right? Now, look, if the positive area up here is equal to the negative area down here, what will be true? When it gets to the end of the graph, it's going to be back where it started. If the positive area and the negative area, because area is displacement, if those two areas are equal, the car or whatever the object is going to come right back to where it started. Does that make sense? Money. Okay, so I have 3 questions. So I'll give you guys like 3 minutes. The first question, I think I'm going to do it right here. The average acceleration from t equals 0, so here's t equals 0, and then here is t equals 20. So how do we find the average acceleration between those 2 points? Just, connect those 2 points. Oops. Like that. Connect, yeah. Well, you'll have a ruler. Connect those 2 points with a straight line. There's t equals 20 right there. And take the slope of that line. And remember, whenever you're taking the slope of a straight line, you can use any 2 points. It doesn't have to be that point and that point. I mean, you could use this point and that point. You know, it doesn't matter. You get the same answer. All right, so the average acceleration is going to be the change of velocity over the time. So let's see, 2 points that are nice. Let's use 10. I'm going to use 10 seconds and 20 seconds. So what's the change? What's the rise? 8. and then the run is 10. So the average acceleration comes out as positive 8 meter per second squared from the start of the graph to the end. Oh yeah, 0.8. Thanks. Okay. Second question. Find the instantaneous, let's revert this back. Find the instantaneous acceleration at t equals 10. What is super duper nice about t equals 10? It falls where? On a straight line. You know, hey, what would you have to do if I asked about this point right here? You'd have to do what? Draw a tangent line, which is kind of hard because that's a tight curve. That'd be a tough one. Okay, so at t equals 10, instantaneous, we're taking the slope of that straight line using any 2 points you want. So let's use that point and that point. We'll use those 2 points. So the instantaneous acceleration is going to be, so the rise using those two is about 5. And then the run is 11, 12. The run is 3. So what's that going to be? 1 2/3, so like 1.7, something like that. 1 2/3. Round to the 10th place. All right, we already talked about this one. The total displacement from start to finish. I mean, you can just you can see it here. So what do we know about this displacement in here? This displacement in that shaded area is what? Negative. This displacement up here is positive, and you can just see that they're the same. So what's the answer to this one going to be? 0. The total displacement is 0. Now, hey, what if I asked for the total distance? Remember, distance doesn't care about direction. What would the answer be for the total distance? Is that what it works out? Are each of those areas about 60? Okay, so if this is 60 meters and then that's 60 meters, that'd be negative. The total distance would be 120. All right, good job.